Welcome along to Datadog on secure remote updates. This is an episode where we're going to talk about some of the challenges that there are in securely and reliably updating large numbers of systems. Just a little bit of administrative stuff before we get started. If you're not aware of the Datadog On series, perhaps this is the first one you've come along to, this is like an engineering-led series of webinars where we talk about some of the challenges and solutions that Datadog has come up with in a variety of areas of technology. This webinar will be recorded and it'll be available on the URL on the page there, which is the Datadog On website. Also, if you have any questions that you'd like to ask as we go through the content, please do use the Q&A section in Zoom. There's also a chat section, but we'll be looking at the Q&A at the end. And if anyone's got any questions, we'll get to them then. So let's get kicked off with some introductions. Arthur, do you want to go first?
Sure, thanks, Rory. Nice to meet, nice to see everyone. My name is Arthur. I've been working at Datadog for about 6.5 years. I'm a staff engineer there. And these days, I'm mostly working on problems related to remote updates in general. And Paul, do you want to go next?
Yeah. Hi, everyone. My name is Paul. I've been working at Datadog for a bit more than 4 years now as a software engineer and working on the topic of secure remote updates for a bit more than 2 years. Rory?
Yep, and hi everyone. Yep, so I'm just helping facilitate today. My name is Rory. I've been on the security advocacy team at Datadog for about just over 2 years now. And in that time, I've kind of focused a lot on container security, cloud security, app security, basically anything security related. So that's us. So let's get started. So the first thing we wanted to talk about today was to look a little bit about the background and talk a bit about what it was that motivated Datadog to take this idea of adding remote updates, adding this ability to make remote updates to our product. So Arthur, do you want to take us off on that one?
Sure. I assume everyone here is pretty familiar with Datadog already, right? So we have an agent that runs on your systems. It collects and submits a bunch of observability data towards our platform, right? So that's a one direction communication, right? From the agent to Datadog, and this is how Datadog worked for about 10 years, right? So we had this purposeful choice in the past to avoid bidirectional communication because it simplified our security and reliability posture a lot, with the trade-off, obviously, that we couldn't build any type of feature that would require this type of bidirectional communication, so sending back data from our backends towards our agents, right? But this changed about 2 years ago, and we started sending data back from our backend towards those agents, with a goal of powering new features, things that would change the configuration of the agent, that would change even update the agent, change some runtime settings, and all these type of features, right? But because of this history of Datadog, right, where we had this purposeful choice in the past not to do this type of stuff, I think we've been like a bit more careful and planning in advance that like some other companies might have done. In the sense that we really looked at the problem and how we could try to solve it, to solve like some of the issues with remote updates in a general sense, right? So there were two main driving factors for us that drove us towards those remote updates capabilities 2 years ago. First is that Datadog is no longer just an observability platform, right? Now it's also a security product. It has security products and it's a security platform. And we introduce new products like we have something like a WAF, similar to a WAF, so web application firewall. We also have something similar to an EDR. That would protect your endpoints. And for this type of security software, as like a user of this software, you want not only to be able to be alerted when something goes wrong on your system, but you also want to be able to act quickly on those systems directly from the the UI of that EDR or of that WAF. So a good example there is if you see an attacker sending you SQL injection attempts, you want to block their IP directly, right? And you want to do this through Datadog, not through a config change locally or something like that. And the second part was as we are growing, so are our customers, and they have more and more complex environments. We have some companies where there's been multiple merger and acquisition, where different companies each had like their different like Datadog deployment setup, right? And now that they've merged, they have very heterogeneous environments where they have like, I don't know, 10 ways of deploying the agent or changing this configuration. And because of that, we realized that at some point we were going to need a more Datadog, like a Datadog way to help them solve those problems, help them change their configuration, or help them update their agents. So now I want to define a little bit what we mean by remote updates, because it's a pretty overloaded term. So basically, it's anything that changes the behavior of your agents or tracers. So you can include software updates, configuration updates, and also like more niche things like security detection rules, runtime configuration, so things like sampling rates or this type of stuff. And you can even include jobs that you would send to your agents or to your tracers. So for us, this is all remote updates because it's a backend driven change that changes the behavior of your agent or tracers. And the reason why we group all of them as remote updates under the same umbrella, I'd say, is because they all bring the same risk with them. First, they bring a security risk, right? As you might have seen in the past few years, there was multiple breaches and security incidents where you had like threat actors that leverage SaaS provider remote configuration or remote update systems in their attacks to attack the customers of those SaaS provider. And the second reason is reliability. And I mean, here again, I think that there's very good recent examples of what can go wrong when you remotely update a system. It's always dangerous, right? Your update might contain something bad. It might crash the components that you're updating, or even worse, it could crash the system that hosts that component. So because of those risks and the history of Datadog, where we didn't have all of this purposefully in the past, what we decided to do for all of those was to build an internal platform for all this type of use case, where we could have a single platform that would basically handle all of those updates for other teams at Datadog. And really, the reason why we did that is inside of such a platform, you can bake in things like telemetry for all of your updates. So you can monitor how all your updates are doing. You can also bake in security aspects inside of this platform. You can also bake in reliability aspects like a gradual rollout deployment inside of there. And it's also a chance for customers that might have like compliance that prevents them from using such features. Since we have like a single pipe and a single platform, they can very easily opt in and out of such features, because it's not something that's distributed across like many different teams' code base, right? There is a single pipe that goes towards the agent. So it's just an on and off switch for whoever doesn't want or cannot use those systems. So really, like this is what me and Paul have been working on, and really our mission as a team is to provide other teams at Datadog a simple way, a secure way, and a reliable way to update their agents and tracers. And on that.
Yeah, so I mean, I think there's a really interesting point that we flagged up there in this thing is that one of the main things we need to make sure with this is that our updates are actually, are going to the right people and are not being compromised or attacked. And I know that for me anyway, as we worked through the process of developing this webinar, I learned quite a lot about some of the different ways in which these things could be attacked and some of the things that you have to consider and actually think about when you're trying to protect them from that kind of thing. And Paul, do you want to take us away on that side of things?
Sure. So if we think about the update flow as a whole, we can find and think about a few different security risks and security constraints this brings. So let's have a look at the high-level flow to understand some of those. So in this high-level flow, there are three different parts. The first one being the update source. So if you want to update something, it needs to come from someone or something emitting these updates. So this create the updates. To simplify a bit the mental model, you can think about the update as a file, for instance. And so once the update source created this file, it's sent to the update platform, which is us inside Datadog. We process it, we store it, and we send it to the last part, which is the customer environment, and more specifically to the agent or tracer, so that the agent and tracer can receive the updates and act on it, do what it has to do with it. Let's focus on those three different parts and see what are the risks and constraints associated with that. So thinking about the update source, there are two different types of sources in our case. The first one is the customer source. So as we mentioned before, we have a feature that we can call the IP blocking, where the customer goes into the Datadog UI, select one of their application and says, I want to block this IP in my web application firewall. So this comes from the customer. And this brings a few constraints. One of them being a bit obvious is we need an authentication system to identify the source, make sure that the customer is who he is, and make sure that this person is allowed to create this IP blocking requirements. Then another constraint here is that we want to make sure the instruction is routed to the targeted web application firewall and not to another application that wouldn't need to block this IP. Another source is the Datadog source. So we have, for example, a feature at Datadog, which is default agent security rule. So we, Datadog, sends security rules to all the agents out there and to all our customers, so they can detect malicious events happening on their hosts, which means we need also an authentication system to identify that Datadog, the correct person Datadog is emitting this new set of rules. And since the blast radius of this is very important because we impact every agent of every customers, we should make sure that it's only emitted by a handful of people that we select carefully, and only them can actually create those security rules. Now that the update is created, it goes into the update platform. So inside the update platform, there is a bunch of different services interacting with each other inside the Datadog backend as a whole. And because how sensitive this is, we want to make sure that the update platform itself is isolated from the rest of Datadog, so that inside every Datadog site, we have control over what is happening between our services. We control the interactions and dependencies between the different services of the platform and Datadog interaction. Once the update goes through the update platform, eventually we need to store it, most likely in a database. So once we store it in a database, one obvious risk and constraint is basically we want to make sure about the integrity of the configurations and the updates, that it's not corrupted. And when we'll send it to the customer environment, it won't be corrupted or tampered. Another thing is that it's a database, so we want to fully define service-to-service authentication and authorization, who can write to the database, who can read from the database, and this actually applies to every service of our platform, knows who can talk to who, basically, and yeah, define the interactions properly. Now, even though we are isolated from the rest of Datadog, we still need to interact with some of the infrastructure for additional feature to power the platform. which is why we need to define network policies inside our infrastructure to explicitly allow every network interactions that can happen between our services and the rest of the Datadog infra. So yeah, these are some of the security risk and constraints about the update platform. But now that the update went through that, we send it to the customer environments, and more especially to the agent and tracer, so they can apply the updates. But here, the major constraints is that we don't control the customer environment at all. A customer might use a proxy, another one might not use a proxy, some might use TLS, some might not, which brings one big constraint here is that we can't rely on TLS for the integrity of the updates. We need something on top of the requests to make sure that the agent and the tracer can verify the configurations. And by verifying, we mean three things. First one is that the updates actually comes from Datadog. Second one is that it reached the correct targets, so that the update is for agent A and not for agent B. And the last one is agent must get the most recent updates and not an update that is 1 year old. So we saw different risk and constraints associated to this platform, but one big focus we want to have is about signing the updates, because the integrity of the update is a big part of the platform. And for that, we can highlight three components. So we want to sign the updates as soon as possible, in our case, at the entry of the update platform, so that once it enters our platform, we can guarantee the integrity of the updates until the agent and the tracer. We want to make sure that the agent and the tracer get the latest version of the updates available. And one last key part is that we have different kind of updates. As Arthur mentioned, we have software updates, configuration updates, jobs, and each one of those brings different constraints on who can sign, how to sign, which is why we need to manage multiple keys to sign those updates. So now that we have everything in mind, let's try to design a first signing pipeline. We can start easy. We have a private key owned by Datadog. We sign our updates and we send it to the agent. The agent is embedded with the public key and can verify that the updates come from Datadog. That's simple, that's easy, but we have one big problem. What happens if the key gets compromised? We need to rotate it, and since the agent is bundled with a public key, it gets very complicated. We want to rotate the key on every agent we ever shipped. So that's a bit complex. So we need to introduce something more in our pipeline. This is something that is done in the industry. We can split the keys. We have one root private key that we stored in a very secure fashion offline that we use to sign a list of lower level keys that we can call update keys, and we send that to the agent. The agent is still embedded with the root public key, so it can verify the list of lower level keys, and then the agent can use this list of lower level keys to actually verify the updates themselves. So we have two parts, the root private key, and then we have the update private keys, which can only sign some configuration type, and these ones are verified by the agents as well. So we didn't fully prevented the key from being leaked, but at least we minimized the outcomes. Though we have one additional problem here, how to ensure that the agent doesn't get an old update, like one that is pretty recent and not the one that is 1 year old. So for this part, we need to introduce one more thing inside the pipeline, which is versioning every file we send to the agents. By versioning, it's in every configuration file, every update file. We start with version 1, and when we send a new update, we go to version 2, version 3, etc., etc. Which means that when the agent receives a file version 10, it will never accept a new file that is version 9, version 8, or below. It will only accept file that will be version 11 and above. This prevents the agent from going back in time and only goes forward in time, which is something that we want. But we didn't quite fully resolve the problem of having a fresh config. Because if we have a new agent, it doesn't have the previous update version. So how do we know where to start and how to ensure that the agent gets a version that is recent and not one that is old? So for that, we keep the same pipeline. And for both of those lines, we include an expiration, which means that if the agent gets an update that is too old, for example, more than 2 weeks, that could be an expiration date, then it will reject the configurations, which means that even if we could send, in theory, older updates to the agents, we can't send updates that are too old, like 1 year old or 10 years old, due to this expiration time. And since we also have the version inside every file, we also go only forward in time, which prevents us from the rollback attacks. So yeah, we want to do that for both the updates and the list of public keys because they both have the same problem of going backward or forward in time. We could include much more security against some of the attacks. And if we do this mental path, we end up by looking what is done out there, and we see that something is called TUF, the update framework, which is a toolbox of defense against such attacks and much more, such as the code freeze attack or a mix and match attack. So we can use that to design our pipeline and make sure we're protected against a list of known attacks. This is something that we already use internally when we upgrade Python integrations. We have a blog post about that if you want to check out. So yeah, TUF helps us solve our problems here. However, there are a couple of limitations with it. First one is that the root key rotation is still challenging. As I mentioned, we minimize the risk of having a key being compromised. But we can still have a key being compromised. We minimize it by having the key used pretty rarely and having it stored in a secured fashion. But in the extreme case where the root key is leaked and the public key embedded in the agent is the key that is leaked, then we need to rotate it, and we still have some hard work to do to make sure that we rotate it properly and that the agents gets the new keys. Another limitation is that TUF is designed with persistent storage in mind. So for instance, with the file versioning, the agent needs to know that it received version 10 in order to reject every update version 9 or less. Which means that this persistent storage is less true for container environments and gives us a bit less security regarding that.
So, I mean, that's obviously a lot of some of the problems that you might look at when we're talking about the integrity of the updates. But with all the best will in the world, we're always going to have the risk of a bad update, right? We're always going to get the risk that some configuration in a specific device, conflicts, or there's some unusual problem there. And so we have to think about, how do we handle that? How do we deal with bad updates? And Arthur, do you want to go through that for us?
Sure. So updates, anyone that has shipped software pretty much knows that you cannot prevent bugs, right? You're going to ship some bugs, it's just going to happen. So when you think about trying to minimize the risk that those bad updates actually make it to your customers or have like a significant impact there, you really want to take a layered approach, right? With multiple guards, right? Like some kind of Swiss cheese approach. So really, like the first things that you can do are the tested classics. Like you're going to implement testing over all the updates that you're going to perform, right? And you want to test them in all the environments that you're actually going to target before they even get merged into any kind of repository. You also want to try to validate those updates, right? So if I'm sending an update that is going to block an IP, I want to check that the IP format is actually correct. If I'm sending an update that changes the sampling value, I want to check that it's not a negative sampling value. You want to perform all those types of check in advance. Sorry. So now, like, let's say that something actually, like a bug actually goes through those two first layers, right? It passes testing and validation. What you want to do next is to limit as much as possible the blast radius, right? It's going to break somewhere, but it's much better if it actually breaks in your staging environment or some kind of non-critical production environment, that if it breaks immediately all your production, right? So you want to deploy slowly, gradually, and you want to start with non-critical environment first. During that rollout process, you want to monitor, right? You want to look at your Datadog dashboards, make sure that the telemetry that's coming back looks good. And ideally, if you can afford that, you should also plug that back into your stage rollout in a way that either blocks the rollout or automatically roll it back. And speaking of automatic rollback, when you make an update, so let's say we upgrade the agent from one version to the next, ideally, like if that update fails, you don't want the agent to not be working anymore, right? What you want is to automatically go back to the previous version. So one thing I will mention is that for us, since we are a platform team, right, that provides this update service to other teams that come and build onto our APIs, our responsibility is more towards the right? We don't really deal with the testing parts and not really with the validation either. This is more for the teams that are actually using your platform. So I will focus mostly on the parts on the right. Starting with stage rollouts. So like if you're deploying service at your company, I'm pretty sure you have something like this, right? Like you don't deploy your service immediately everywhere in production. You're probably going to deploy it to some staging environment first, then you're going to monitor either automatically or like looking at it yourself, that everything looks good inside of that staging environment. And only then will you start deploying that change to your production environment. When you also deploy those changes, you want to do it slowly. So let's say you want to go from 0% of your instance to 100% in 10 minutes on staging, and from 0 to 100 in 60 minutes in production. So that's a very naive stage rollout, right? This is fine for small blast radius. Like if it's for one small service, it's fine. And you're working in a startup, it's fine. But if you start to roll things out to a much wider audience, to let's say like a million instance or more, then you probably want to be a bit more careful than this. So one example I can give you is, as Paul mentioned earlier, we have our EDR product that receives security detection rule updates, right? And that's a pretty dangerous type of update. So we want to be particularly careful about this one. So in this type of context, you probably want something that has much more steps, where you're going to confirm that the updates work in all your environment, really starting with the less critical and ramping up. So in our context, it looks a little bit, it's not 100% accurate, but it looks a little bit like this, where we are first going to start with a canary inside of staging. Then we're going to continue with the rest of staging. Then we have this notion at Datadog that you might know about that we call site, where we don't have a single instance of Datadog that actually runs. We have multiple completely isolated instances of Datadog. So we are going to roll this out one instance at a time. And what we are actually going to do first is, because Datadog uses Datadog, we have a unique opportunity of doing a dog fooding rollout, where we are going to deploy this new change to ourselves first. So that way we can actually be impacted first before our customers are impacted, which is usually desirable. Especially because we have more control and we can start with a canary in there, right? So we know which part of our infrastructure are less critical, so we can target that first, test with actual production, even if it's less critical production, and then ramp things up across our services. And the final step is obviously to roll out customers for the customers. And here again, we are going to follow this side-by-side policy, and even inside of those sites, we are going to go slowly. So in terms of how you can implement such a system, right? So the way the update platform works is you have a bunch of agents out there running on your customers' infrastructure, right? And they are constantly polling our backend, asking it, do you have an update for me? Do you have an update for me? And with that request, they also send all the metadata they have about themselves. They say, okay, I'm host whatever. I mean, my host name is whatever. I have this set of tags, etc. And our backend is going to take all of that information and check if we have any updates for that particular agent. So basically, implementing something like a rollout where we say, okay, we only want to send this update to the staging agent is pretty easy. All we have to do is, in the update platform, we can attach an expression to each of the updates. So basically a filter that says for which agent you want to send this particular updates. And then our update platform, every time a polling request comes in, we can evaluate this expression and say, okay, this agent matches the expression, I'm sending it the update, or it doesn't, I'm not sending it the updates. The more tricky part there is, how do you do this where you progressively roll this out over 10 minutes, right? Because for something like a tag, it's very easy to write such an expression. You just put this little expression and you're done, right? But how do you do it progressively, where two different agents from staging, you want to start with one first and then with the second, but slowly, not at the same time. You have a first option that I think is the most natural and most people will probably reach out to first, which is you can just track all the agents that are connected to your systems, right? So you add a separate database where you store just the list of connected agents, and then you're going to add them one, like you're going to mark them one by one as they should receive the updates over the 10 minutes. So basically, at the start of the rollout, there is no one in the list of the agents that should receive the update, and at the end of the 10 minutes, you have everyone. This works, but there's a few cons there. So first, we obviously added an extra database where we have to keep state, right? We also have so we have an extra dependency. It's going to add a bunch of latency and complexity. But what you also have to realize is that we don't really control the deployments of agents at our customer, right? So it makes it a little bit more tricky because the list of agents that are out there is constantly evolving, and agents are popping up and out of existence all the time. So it's a bit hard to converge to a state where we have all agents inside of that rollout database to mark the rollout as complete. So instead, like what we usually do in our update platform is a little trick that allows us to keep the old design that we had in the first slide, where we don't need to store any extra state. And basically, the way you can do that is take something unique about the agent. So we have an ID that is available called the host name, right? Every single agents are going to have one since they are on different hosts. And what we can do with this host name is take the hash of the host name, do a modulus 100 over it, and this is going to give you a number between 0 and 99 for every single agent. And if you have a good quality hashing function, you should have a pretty good distribution. Like you should statistically, like they should have all about the same chance to be 0, 1, 2, or 3, or whatever. So then what you can do is like have a like you can increase your percentage. So say you want to deploy to 25% of the agents. All you have to do is actually check that this hash modulus is under 25. So yeah, now we have a way of doing this in a completely stateless way. All we have to do is to keep increasing this 25 to 26, 27 as time passes. And yeah, and this is a much simpler solution to implement, even if it has a few cons. And the main cons that you have is that it's a statistical approach, right? Like it's imprecise by nature, and like even if you say I only want to deploy to 1%. If you have a small environment of 3 agents, it's possible that you're unlucky and that all 3 are going to get the update immediately, because all their hash ends up being 1, right? So yeah, so you have to take that into account. But when you roll things out to millions of agents, this is not necessarily an issue.
So yeah, I mean, that's obviously a good lot about how we can stop these things happening, how we can detect it as well quickly. But obviously at the individual agent level, you know, we've got one of these bad updates. We're going to have to try and back off. We don't want the agent to crash. We don't want the machine to crash. So we need to think about how we can do automatic rollbacks. And Arthur, what do we do there?
Yep, exactly. You want to minimize the impact locally. So let's look at how. So the example I'm going to use for this is the like remote updates of the agent. So we want to we have an agent running on the host, right? That is at version 750. And we want to upgrade that agent to version 751, right? So the way you do that locally, like without any kind of remote updates, right, is you just run apt install Datadog agent, right, and it's going to update. And if there happens to be a problem, right, you notice that anything is weird on your dashboard with this new agent, it's not sending a metric you expect or anything like that, you can just rerun the command with the old version and roll this back. And I'm saying apt install directly, but it's also valid with your Ansible, Puppet, whatever way you use to deploy the agent. But now, like, I mean, for the remote updates, I guess we can just do the same, right? So we send a remote order where we say, okay, install version 751. The agent runs the equivalent command to update the agent to 751. And then, like, if we want to roll back, we can just send the reverse order, right? Well, not really, actually, because if your agent update is bad, right? So you're now on version 751, but it can't start, for example, like it crashes at boot. How are you going to communicate with it to send it the order to roll back, right? So it's a one-way door, right? So like when you send the updates, if anything catastrophic happens on the other side, you're going to lose connection with that agent, and you won't have the opportunity of actually updating it back and rolling back the version. And then you have to contact your customer and tell them, oh, sorry, we messed up. You have to run this command to fix your system. So obviously, this is really not desirable, even like especially when you look at like all the different failure scenarios that can happen, where this can happen, right? Like I mentioned startup crashes, but the networking logic could be broken. You might have very bad performance issues. Or for example, like we were talking about TUF earlier, we bundle a public key, maybe we bundle the wrong public key, and then we can't communicate, like we can't validate the updates that are coming from the backend. So now we think every command is an attack, and we can't communicate with that agent. So we need a better model, and we need a model that is a two-way door where we can recover in case there is a failure. So internally, we call this model running an experiment. The goal is the same. You want to go from version 750 to version 751, right? But here you're going to add an extra middle step, right? Like in between the version 750 and the version 751. What you're going to do in that intermediary step is to first install that version 751 in addition to the version 750. So both are going to be installed at the same time. Then you're not going to immediately go to the version 751, and instead you're going to monitor that agent for 5 minutes or 10 minutes, just making sure that it's actually working fine. So now, let's imagine that everything looks good. The backend will see that the new version of the agent is running. It sees that it's the experiment version, that it performs maybe a little health check from the backend, and everything looks good. The monitors all passed. Okay, after 5 minutes, we can promote. So we remove the old version, and we just say, okay, the new stable version is this version 751, right? What is more interesting is what this gives us in case of failure, right? So as I explained earlier, we can't really just send a remote instruction to roll things back, right? So what we are going to do instead with this system is now we have a version to fall back to locally, right? So what we can do is add local triggers that do not need any communication with the backend, and that are going to automatically roll back the agent to the previous version if anything looks weird. So the most important of those triggers are timeout and crash detection. So if you have a crash, you want to immediately fall back, because if not, you're going to have like a loss of observability or this type of stuff. But the timeout is even more important, because if you lose communication with the backend, right, it might be hard to detect from the agent standpoint. Maybe like the public key is wrong, and we can't really tell the difference if it's an attack or if there's a problem. So you really want a timeout where it will automatically fall back to the previous version. And basically, like the promotion is the only way to get out of this timeout, right? So when you start this experiment, there is only two outcomes. Either you hit the timeout or any other of the triggers and you roll back, or you receive from the backend another order that tells you, okay, everything is looking good, and you can proceed. And this is very powerful, because you basically can't lock yourself out with such a mechanism, since the promotion order has to come from the backend. It means the new version is able to communicate with the backend and works at least somewhat properly, right? So it's a very powerful system, but it does still have a few limitations, right? Like you can imagine that if the experiment logic itself does not work properly, you can still break the agent. That's still fully possible. And the other drawbacks is that you do require twice the disk space during a few minutes, even if we are looking at ways to reduce that a little bit, because a lot of files are duplicated between versions, but that's another topic. Wait, I have a little pop-up that prevents me. Okay, so now like that system looks very complex. So how do you actually go and implement this? It's actually much easier than you would expect, at least on Linux, thanks to the power of systemd. So this would be your initial state where you're with version 750 installed on your system, right? So people that have worked with Linux probably will probably feel at home. You have like the agent that is installed on the disk, so version 750, and you have a unit, a systemd unit whose job is to run the agents pretty much. So for Windows folks, this is basically like a Windows service as well. Like it's the way on Linux to have a daemon that is going to be running and that is going to be restarted if it crashes. Systemd is the service manager. So systemd is in charge of executing the agents, and we can actually use it, leverage it to have this experiment logic. So the way we are doing that is when we start an experiment, we are going to install the new version of the agent, right? So now you have version 751 on your file system, and we have a symlink that points to it for convenience reason called experiment. And then you're going to have an extra systemd unit that we call agent experiment. And what you can do with systemd units, is say that two units are going to conflict. So agent is going to conflict with the agent experiment, and agent experiment is going to conflict with the agent. So you can't have both running at the same time. It's one or the other, right? So to start the experiment with systemd, all you have to do is to start the unit, right? So now you have the experiment running, right? But what happens if it actually fails, right? And this is where you really get the power out of systemd, because you can very easily on the unit of the experiment say, okay, if my agent experiment unit fails, I want to fall back to the agent unit, right? And also set a timeout where if the agent experiment unit runs for more than 5 minutes, or 10 minutes, sorry, you're going to automatically fall back to it's actually going to fail, and the on failure will trigger the rollback to the previous agent version. So basically, we are delegating this failure handling completely to systemd. And we don't even have to deal with it at the agent level, like systemd does everything for us. And with this setup of conflicts and on failure, we basically get a guarantee that we will roll back to the previous agent version if there's any crash or if we reach the timeout. And now, like, if you want to promote the experiment, right? The experiment succeeds, you want to promote it. It's also very easy to do that. All you have to do is to update the stable symlink. You can remove all the stuff that you don't need. So the old version, the experiment symlink, and the systemd unit for the agent experiment. And then you can just restart the agent running, the agent unit, the main agent unit, and have it running. And now you're complete. You're back in your initial state, except you have an up-to-date agent. And yeah.
Cool. And so that is, I think, a lot of what we've had to consider when doing this. If anyone's got any questions, please do put them in the Q&A section. There is one question that I had about this. I think one that's interesting is, when you're talking about the experiment system, does that essentially have to be implemented per like systemd? So in Windows, you need to use a service, or basically per initial init system?
Yes, today that's the approach we've taken, because it's let's say the most reliable, right? Because the fact it's a third party, right? Like, it's a different software from Datadog, and it's like the service manager itself. Having the experiment system inside of the service manager makes it much more reliable, right? Like we could write our own like subsystem manager where we have like some kind of like mini systemd or whatever that will actually handle the processes of the agent and like switch from one to the other if things go wrong. We might do that someday, but it's like, it's much better to use the tried and tested like service manager for this. And yes, this is something you're gonna have to do like per platform. Like, the implementation on Linux is different today than our implementation on Windows. So yeah.
Yeah. So yeah, one that I think scales, and I suppose if you get some unusual things without system initialization, could be challenging. Great. Well, thanks very much for that. I think that's going to be a wrap for today. And thanks very much for people coming on. And if you're interested in hearing more of Datadog on, as I said, the website is there. And if you're watching the recording, you should be able to get more information there as well. So I will, with that, stop sharing. And that's great. Cheers. Bye.